quantum mechanics. In previous presentations, we discussed the findings of quantum mechanics, and these findings can be so impressive that you might even forget that it's incomplete, is that it's not actually providing any answers to the questions it poses. For example, we don't actually get any closure on how the Hamiltonian operator selects one eigenvalue out of this eigenfunction, out of this abstract space of potential represented by the quantum wave function. So clearly there's a lot of conceptual problems with our modern views of quantum reality. But to understand this, first we have to understand why the modern picture broke, what it was about quantum mechanics that caused us to not be able to accept the classical universe. Because a lot of people would much rather, instead of dealing with all this quantum crap, to just say, we live in an objective universe with cause and effect, and everything is determined, and it follows a precise trajectory that we can predict using our mathematics. And that is how scientists prefer to think about the world, because scientists are, in general, actually a pretty conservative lot with respect to their own endeavors. They don't want to be disrupted. They don't want a new framework to think about the world. They'd rather stick with their own ways. So modern physics still needs to give us a single metaphor for how the universe works. And we don't have that. We don't really understand. There have been a number of attempts throughout history. For example, 5 minutes after the invention of the wheel, everyone was like, the world is like a wheel in an endless cycle of eternal recurrence. And then books came around and they were like, the world is a book. God is the author of being. And in the beginning was the Word. The Word is everything. And then 2 minutes after clocks came out, they totally got over the Logos. They got over the Word, and they said, God is a divine watchmaker. The world is a big machine, and God wound up the earth and wound up creation, and everything mechanistically unfolds on a predetermined path by the laws of motion that are created by God. But however, quantum physics has broken the modern paradigm. It's broken not just the mechanical view of the world, but all of our views of the world. We don't know what to make of quantum mechanics. We have all these different interpretations. We have an entire industry, which we'll talk about, which is cropped up of trying to interpret what the hell quantum mechanics means for our reality, means for the world we live in. But the basic answer is we don't know. So the prevailing doctrine actually of establishment physics is that there is no ultimate reality. There is no reality deeper than the quantum level. So there's no explanation, there's no creation that happens below what we can observe. The quantum world, it's just too funky. There is no deeper reality. There's nothing that's explaining why, reality picks one value out of this entire operator. It just does. There's no real explanation. And that's pretty much how physicists think about the world. It's that it's basically random. And the dangers of this view are corrosive in the extreme. And the reason for that is because, and it cannot be overstated, it's basically applying a principle of indifference. Since there's no positive reason for assigning different probabilities to different statistical or predictive assertions, equal probabilities must be assigned to all. And it's a little bit more complicated than that because it's ascribing different probability amplitudes to different functions in different positions of the quantum particle. But basically it's saying that it has this probabilistic structure and it just selects the thing that is most probable. And so the question is, like, how does that get to anything interesting? How does that cohere? How does that correspond to the actual world, which we can see that we're actually living in, which has all of this marvelous self-organization and emergent features like life and consciousness? How does any of that emerge basically out of a random structure? And that's a very good question. That's not really something that physicists are used to thinking about. Some people now might see the world as running like a computer, as in it's one large algorithm or simulation that's run somehow using the quantum mechanical world. So basically, the up and down spins of an electron can be thought of as the ones and zeros in computation, and the entire world can be reduced to this bit computation, just like in principle. The world is no more complicated than a game of Mario Kart. It's more than 8 bits, but basically all that it's doing is ones and zeros. And that's basically how some of the so-called cutting-edge physicists are thinking about the world, is in terms of information and computation. But insofar as quantum mechanics must give us a general view of the world that transcends the distinctions among common classical and modern worldviews, we ought to recruit the tentative images of the world proposed by quantum physicists to explain the world's cyclical, linguistic, mechanistic, informational, and computational aspects all at once. So that means we can take multiple different interpretations, synthesize their best results, and actually correspond that to reality. And that's when we do that, we're doing something which we'll talk about later, which is quantum metamechanics metaformalization, which basically means we're mapping the findings of quantum mechanics into the metaformal system, which is the intrinsic language of reality. And then we are explaining ourselves on the basis of that reality for basically how things work. And just like, when we had computers, we needed to update our model of reality to think about these informational and computational aspects. With the rise of synthetic intelligence and a new era of humanity, our dominant vision of physical reality must also be updated to reflect changes in our knowledge and understanding. Just as classical mechanics, which is inarguably among the most significant and most successful theories in history, but when problems arose that couldn't be solved within its conceptual framework, it had to be extended into a more general theory called special relativity, in which classical mechanics holds as a limit in case for motion well below the speed of light. So basically, for most cases, classical mechanics works, but we needed a generalization of quantum mechanics in order to explain some of the facts about observers in very fast motion and how time might actually diverge from itself in space-time. We actually have to quantize relative to a fixed point of reference rather than just having it be a free-for-all. So next, to accommodate for the curvature of space-time needed to give rise to gravity, Einstein quickly formulated general relativity, which is, again, another generalization of his special relativity theory, in which the flat 4D manifold of special relativity holds as a particular limit, and then another extension of the inability of any framework to and then another extension is formulated to actually think about the world in terms of space-time curvature, that then the masses of objects are able to actually respond to the dynamical patterns of the universe, and thus the matter is telling space-time how to curve, just as space-time is telling matter how to move. So there's actually a feedback relationship between space-time and matter, which actually is self-generative and self-referential. So matter is part of space-time, and it is actually informing itself. So space-time can be thought of as informing itself on how to curve and move. So, however, despite the best attempts of physicists over the last century to reconcile quantum physics and general relativity, most efforts have come up short because they are, to some extent, mutually incompatible. So if we think of quantum mechanics as a third generalization after general relativity, but then we have run into some problems because quantum mechanics doesn't explain general relativity better than general relativity does. It actually breaks a lot of it. For example, we'll talk about in quantum mechanics, we need something that looks like faster than light travel of information in order to account for something called quantum non-locality or quantum entanglement. So the problem with this fourth extension is that general relativity and quantum mechanics are not reconciled to one another yet. So a fourth extension is needed in order to reconcile these together, to reconcile the second and third generalizations, somehow seeing both quantum mechanics and general relativity as the global and quantum levels of a more general framework that provides the two theories with common structure and processing. So we are going to have to embed these two different frameworks for thinking about the world, and there has to be a common structure that extends over both of them. So the first attempt at really trying to understand what was going on with quantum mechanics was called the Copenhagen interpretation. And this was a bunch of people, for example, Niels Bohr, Werner Heisenberg, all these people who then went on to win Nobel Prize and really pioneer what we know of as modern physics, came together. They went to Copenhagen. They went to a physical location and said, okay, we're going to spend this summer and we're going to figure out what the heck's going on with quantum mechanics. And so the quantum mechanical view of an atom that they eventually kind of realized is that an atom isn't just like you see on these like charts in grade school where it's like, oh, it's like the solar system where it's like, oh, there's one shell of electrons and then the next one and there's the orbits around that. No, it's actually much more intricate than that. The quantum mechanical view of an atom says that an atom always has definite values for its position and momentum once it is measured, but in between acts of registration, the particle turns into a quantum wave function representing a space of expansive potential. And so it's said that the wave function selects the position and momentum of a quantum particle and then decoheres into a general position or momentum. However, the particle has no definite attributes between measurement events. We know this, we've been over this, but only a space of likely positions and momentums. And that's represented by the square of the quantum wave function. At any point, we can take two values and say the area under that curve between these two values is the probability that there's going to be a quantum wave function. The entire probability density function sums to 1. So you can just divide whatever you have by 1, and that is the likelihood that that particular space of values is going to align with the eventual position of it. So we know probabilistically where quantum objects are going to end up, but we can't actually figure out exactly where they're going to end up like we can in classical mechanics. So Heisenberg's uncertainty principle says that the more that you know about a quantum particle's position, the less accurately you can predict its momentum, and vice versa. So all interpretation of quantum mechanics are reactions to the problem of quantum wave function collapse or wave-particle duality. Nobel Prize winning physicist Richard Feynman says, quote, "I think it's safe to say that no one understands quantum mechanics. Do not keep saying to yourself if you can possibly avoid it, but how can it be like that? Man, because you'll go down the drain into a blind alley from which nobody has yet escaped. Nobody knows how it can be like that." And yet this weirdly anti-scientific attitude expressed by Richard Feynman, and also held by many other prominent physicists, is against the spirit of science and free inquiry. If we are to progress on the cutting edge of physics, we have to keep searching. We can't just throw up our hands and say, "Oh, we'll never know." That's against the spirit of knowledge and science and truth. We have to have a coherent picture of the quantum world, and that has to be a major goal of science. So most modern physicists hold that the Copenhagen interpretation of quantum mechanics, which states that an atom's attributes are generated in the act of registration, is basically the correct way of looking at the quantum reality. So as quantum physicist Nick Herbert said, one of the best kept secrets of science is that physicists have lost their grip on reality. They don't actually believe in reality below the quantum level or anything that supports it. So they basically just think that the world is a world of appearances. Though news of the reality crisis has hardly yet reached the general population, the impact of our lack of scientific understanding concerning the nature of profound reality cannot be overstated. Scientists have many conflicting, seemingly absurdist tales about how the quantum world works, yet none of them have penetrated to the venerated level of an accepted theory in physics. So we do not have a clue. The physicists have not figured this out. It's been almost 100 years since the Copenhagen consensus meeting, but still, we've yet to really understand deeply what quantum mechanics is and what it means for our picture of reality. So in the following presentation, we'll briefly explain the various theories accepted by physicists and how they align and or conflict with the theory of quantum metamechanics created by Christopher Langan. Thank you. God bless. Take care.